इलेक्ट्रोस्टॅटिक्स मध्ये आज आपण पाहणार आहोत इलेक्ट्रिक फील्ड इंटेन्सिटी ऑफ इन्फानाइट लाइन ऑफ चार्ज.
In the application of Gauss theorem, second application is to find the electric field intensity of the infinitely long straight charge wire or infinitely long charge cylinder having the charge density, that is charge per unit length lambda. Okay, so we want to find the electric field intensity of this charge wire. So what we did, we taken the one charge wire. This is a charge wire on the surface of which charges are uniformly distributed. The length of wire is infinite, okay, and the lambda is the charge per unit length or the linear charge density of the wire. Radius of the wire is capital R, which is not important here, and this is the axis of the wire. We want to find the electric field intensity of this charge wire at the point P, which is at distance small r from the axis of the wire. Okay, we want to find the intensity at the point P. Intensity, electric field intensity at the point is shown by capital E. So we know that if you want to find the intensity at the point P using the Gauss theorem, first you have to draw the Gaussian surface. So here I have drawn the Gaussian surface in the form of the cylinder, Gaussian cylinder. The Gaussian surface, which is a Gaussian cylinder, is passing through the point P. Okay, it is passing through the point P and its length we have taken small l. If L is the length of the Gaussian surface or cylinder, then it means that it encloses the only L length of the charge wire, and on the N length of the charge wire, as per the formula lambda is equal to charge per unit length, the charge will be lambda into length. So if the Gaussian cylinder is of length L, it will enclose the L length of the charge wire. It means it encloses the lambda into L, the total charge of the charge wire. Okay, why we had taken the Gaussian cylinder? Because the wire is of a cylindrical shape. Why we are not enclosing the entire wire? Because entire wire is of infinite length, so we are taking only the part of the wire. We will see whether the part of the wire is important or not in the derivation. Okay, then we have taken the element ds at the point where you want to find the electric field intensity. So element ds, the area vector ds and E are in the same direction, so angle between them is 0. After taking the area element ds, we had written the formula of electric field intensity for this element ds. So electric flux through the area element ds is d phi is equal to E ds cos theta, theta is equals to 0. So d phi is equal to E ds cos 0, that is d phi is equal to E into ds, the equation number 1. Now we have taken the area element on the curved surface of the cylinder. We had not taken the area element on the plane surfaces of the Gaussian cylinder, because here if we take the area element, the ds area vector and intensity vector will be perpendicular. So here flux is 0. Flux here is also 0. Flux through the plane surfaces of the cylinder, of the Gaussian cylinder, is 0. Only flux is important or non-zero for the curved surface. So to find the flux through the Gaussian cylinder, we take the integration of the equation number 1, and electric flux over the entire Gaussian cylinder is phi is equal to integration of d phi. Put the value of d phi. So phi is equal to integration of E ds. E is taken outside the integration as it is a constant. It is same over the entire Gaussian cylinder. So integration of ds. But integration of ds is equals to the surface area of the curved surface of the cylinder. So phi will be E into surface area of the curved surface of the cylinder. So phi is equal to E 2 pi RL. Why 2 pi RL? Because it is a curved surface. Okay, so if you cut the curved surface and open it, it will looks like a rectangle. So we have taken the circumference of this cylinder, which is a 2 pi r, and length is L. So 2 pi RL will be the area of the curved surface into E. This is equation number 2. Now we apply the Gauss theorem. Gauss theorem says that the electric flux over the entire surface is 1 upon epsilon naught times epsilon naught k times the charge enclosed by that surface. So phi is equals to 1 upon epsilon naught k lambda into L, where lambda L is the charge enclosed. So put this value in equation number 2, or using equation number 2 we get 2 pi r L E is equals to 1 upon epsilon naught k lambda into L. So LL cancel. So 2 pi r E is equals to lambda upon epsilon naught k. So as a result, E will be lambda upon 2 epsilon naught k r. This is the electric field intensity of the infinitely long charge wire having charge density lambda at the point which is at distance r from its center. Now in this equation, length is not present. Which length? The length, the Gaussian cylinder length or Gaussian surface length. So it's not important how much part of the wire you had considered while calculating, but it is important what is the charge density or linear charge density. So A is equals to lambda upon 2 pi epsilon naught k r is the electric field intensity of the charge wire at the point P.